So welcome again, good afternoon again. I'm really excited to introduce you the next speaker that we have this afternoon. So for me, he's a myth, and I think that for everybody, he's a myth in the world of energy. And actually, all the things that I know, mostly all the things that I know in the world of energy come from his video. So sorry for the introduction if it's a bit too long, but it's something that I need to do. So he's the research director at the National Research Council in Bologna. He is a member of the Italian National Academy of Sciences. His research concerns molecules and materials for solar energy conversion and the study of the energy transition to more sustainable models and technology. He has published over 250 scientific papers and 11 books. He serves as consultant on energy and resources for international institutions and companies worldwide, and he has received several scientific awards, and is committed to advise people that science and technology alone cannot warrant us a sustainable future. I'm speaking about Nicola Armaroli. Welcome on stage.
Thank you very much, Silvia. I removed this one. And thank you for this invitation. This is my title, and you know I have 30 minutes to talk about the energy transition, and it's going to be a very tough challenge, 30 minutes to talk about this complicated topic. But I try to do my best. I hope it will work. It works. So this is the title. So let's put it in the context, why we are here discussing this. It has been already reminded during this afternoon, but let's recall some numbers. More than 80% of the the world primary energy supply comes from fossil fuels, okay? So we burn every year 50 gigaton of fossil fuels per year, 50 billion tons, okay? This generates 34 billions of tons of carbon dioxide per year. Please note that the waste is more than twice as much compared to the fuel, because you combine it with oxygen, okay? So that's very important, never forget. And about 50% of the carbon dioxide is digested by the biosphere, particularly from the photosynthesis, but the rest accumulates in the atmosphere. So the global warming is on the rise. We have an average anthropogenic contribution to global warming, which is 1.1 degrees compared to pre-industrial levels. And our target now is to stay within 2 degrees. So the climate situation, never forget it, is going to be much worse even if we do our best, because 2 degrees is almost twice as 1, and the Earth is not a linear system. So adaptation is needed. Never forget this. We have to adapt everything. The new developments that we made, the real estate, never forget adaptation. So we have a complex energy transition with several constraints, chemical, physical, which I don't have time to tell you about, but let me tell you the main transition constraint that we have, which is time. Time to avoid climate disaster is very limited, and the window is shrinking day by day. Time to phase out present technologies is very long, because fossil fuels are incorporated everywhere. Look at this concrete building. This is a monument to fossil fuels. And the time to deploy new technologies is typically very, very long. And for example, it took 68 years from the invention of the silicon photovoltaic cell to the deployment of 1 terawatt of silicon photovoltaics around the world. It's a long time. What is the root of our energy problem? It is fire, okay? If you can use only one word, it's fire. Why fire? Because we burn too much. We burned yesterday in the caverns in the Middle Age, and that was, understandable. But we keep on burning today in our supposed to be modern civilization because we burn to eat, to move, and to make electricity. And we have already the technologies to do this without burning anything. And the main way out of it is electrification. And so we have to move from molecules like methane and gasoline to electrons. And this is what we discussed in this paper 13 years ago, when it was quite naive, the idea of moving towards an electricity-powered world. Now it is a well-shared concept, but that time was not like this. Why we have to do electrification? Because electric machines are far more efficient than combustion counterparts, and because we have already the technologies which are decarbonized, which are electric, of course, electric renewable technologies. And they are already on the market, and they are already the most competitive. They are the cheapest one. That's very good news. If I have to tell you about the phasing out of fossil fuels, I need this diagram, which represents the American energy system, US. The European is not that different. On that side, you have all the sources, from petroleum all the way to solar, up. And then you have the sectors of use of energy, which is electricity generation, the orange square, and then you have residential, commercial, industrial, and transportation, the 4 pink boxes, okay? First, information. 67% of the energy entering the US energy system is lost. It is basically lost as heat, okay? And that's highlight again that we have a combustion problem. And only 33% gives an energy service to people. That's the first news. And then let's focus on fossil fuels. If you take coal, which is the black, the gray box there, and you follow the black line, you see that most of it goes to electricity generation. So if you want to coal exit, you have to make renewable electricity, okay? If you want to get out of gas, it's more complicated. The blue line goes in several ways. A lot goes to electricity generation, and the rest goes to heating, residential, industrial, and commercial. And so if you want to implement a gas exit, you need renewable electricity and heat electrification. Third, the most simple one, petroleum, the green line. 80% of petroleum goes to transportation. And by the way, 80% is lost, is rejected, because combustion engines are very inefficient. 80% of the gasoline you put in your tank is lost. It doesn't move your wheels. And in order to decarbonize and to make the oil exit, primarily you have to make transport electrification. And that's why we are here tonight. So the energy transition is primarily about renewable electricity, which is several sources and technologies. You see the pictures. I don't need to describe you what I'm talking about. We have at least 5 choices. And we need an electrification enabler, which is the grid, which is essential. And the grid allows the producers and consumers to be physically connected. And this opens unprecedented opportunities in terms, thanks to digitalization, to connect all of them and to control demand and supply. This is not doable with our present energy system. Your furnace at home is not connected to the other one. Your gasoline car is not connected to anything. So it cannot be a part of an intelligent system. The grid, however, needs to be stable, imbalanced, and constantly updated. And this requires investment, for example. The grid needs to be strong, resilient, and also preserved by cyber attacks, because this is a growing problem. So overall, we need to say that the grid requires massive upgrades and investments. And this is what we are already doing. Somebody says, well, it's too expensive, we cannot do it. That's not true, okay? Because according to the International Monetary Fund, for instance, last year, we put $7 trillion, $7,000 billion in direct and indirect subsidies to fossil fuels. So it's a matter of to decide where we want to put the money. So it is basically mostly a political decision, okay, about the use of the money. Okay, let's go to the transition. Where are we now? If you take the 3 main energy carriers, heat, fuel, and electricity, this is the situation. About 50% of energy goes to make heat, to buildings, to industries, and so on. About 30% goes to fuel, typically liquid fuels for transportation, and here you have mainly transportation. And the good news is that electricity, which is the lowest part of it, but 30% of it is already renewable around the world. In Italy, we know that it's 40%. That's very good news. The other one are very small numbers. So the transition is essentially make these 3 numbers down there bigger at the fastest possible rate while electrifying. And these two here are definitely, most of them are not electrified, so we have to electrify this part. What is the electricity production trend in the last 10 years from 12 to 22? The electricity demand around the world increased by over 30% in a decade, which is absolutely staggering, okay? But there are also good news, because if you see the share of fossil fuels, in absolute terms, the fossil fuels have increased, but in terms of share, they passed from 68 to 61%. So tell this to the people who talk about coal, China using coal and so on. But the number most surprising is the yellow one. The renewables, in particular, solar and wind, passed from less than 3% to over 12% in a decade. So a revolution is taking place. And you see also in terms of new generation capacity, which are the numbers. From 12 to 21, you see that the yellow and blue part, you cannot read it, especially down there, but the yellow and blue part is photovoltaics and wind. And you see that it is increasing dramatically. And now over nearly 80% of new electric capacity around the world, globally, is photovoltaics and wind. Tell to the people that say that they do not count. And, very interesting news, the International Energy Agency told us a few months ago that in 2024, so in a few days, we can say almost, renewables will produce more electricity, I'm talking about petawatt hours, okay, than coal around the world. So renewables are going to be the big player, the #1 player in the world next year. The two dominators are PV and wind, and if we can see we can see here the amount of wind installed in the last decade, and of photovoltaics, they are around 1 terawatt each. But I'm not interested to know how much photovoltaic panels have been installed around the world. I want to know how much electricity they made, okay? And if you look at it globally, you take the average world capacity factor, the capacity at the end of last year are equivalent to 600 nuclear or coal power stations by 1 gigawatt. So remember, wind plus photovoltaics at the end of last year, more than 600 1 gigawatt power plant. Let's look at a practical case, Italy. Italy last year produced about 10% of its electricity by photovoltaics, 10%, okay? And this year, we are going to 30 gigawatt installed at the end of the year. We are going to have 35 terawatt hour per year with the capacity installed at the end of this year. So if you look at wind, this is the wind capacity at the end of this year. This is the production, not very high capacity factor in Italy, unfortunately. Anyhow, PV plus wind in Italy makes up 56 terawatt hours, okay? I just want to remember that there was a plan in Italy for nuclear energy 10 years ago, 12 years ago, and the idea was to make 4 big reactors which were supposed to produce 50 terawatt hours. We have been talking a lot about it, blah, 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 and we did nothing, you know, zero delivered. While people were talking about this, PV plus wind delivered 56 terawatt hours. Never forget it. In Europe, PV plus wind last year overtook the electricity production by gas. So these things are already happening. It's not a dream. We will have it in 20 years. It's already here, okay? Wind plus PV more than gas. The big winner is photovoltaic. The photovoltaic panel is extremely boring. It doesn't excite anyone in terms of what a smart technology. It's very boring. I admit this. But let's look at this very boring panel. According to International Energy Agency, in 2010, photovoltaics is the yellow line, was basically zero. In 2027, photovoltaic will be the most installed technology in the world in terms of capacity installed. It will overtake coal in terms of capacity installed. And this is just amazing. I mean, not one, even myself, 12 years ago, I would have bet a penny on the fact that we would have this trend. So every curious people must think and say, what's going on? Why this happened? And they realized that this happened because photovoltaics combine a long list of things all together which are unique. Let me give you very quickly. They have a standardized production and recycling. Panels are all identical wherever you make them. They are modular. It's the same tile on a roof here or in a gigantic facility in the desert by 2 gigawatts, for example. It has a steadily declining cost, still declining right now, and affordable to millions, billions of pockets already. It has a low critical materials risk. The transportation is easy. It can be loaded either on a big ship or on a camel. You can load it everywhere efficiently, and it works. You can, you can install it everywhere, from a mega city to the village. It's unique, you know. Installation platforms are readily available. People, when you have to install a big energy facility, the first question is, where do I put it? And it's a problem, whatever technology. Here, in most cases, the platforms are already there. Look at this roof here. It does not require ultra-skilled labor, which is important as well. It has no moving parts. That's trivial, but it's very important. Long life, low maintenance. It can be paired with another modular technology, which is battery. It has a high social acceptability. You will never have a technology combining all of this, and that's why you have like this. Let me make some debunking. Okay, if you use a lot of photovoltaics, you will be buried by photovoltaics panel in a few years. That's a myth, you know. This is a paper on Nature Physics last month showing that the amount of photovoltaic waste, let me show you with my finger, is this one by 2050, and the other one is a lot of other waste like coal ash, plastics, municipal waste, and so on. So the volume is not a problem, okay? Renewables require mineral materials, resources, of course, because sunlight is an overabundant extraterrestrial input, we know that. But it's useless as such. You need converters and accumulators of renewable flows to use this energy. So are there enough mineral resources for the energy transition? And that's a topic as a chemist for me is very important. There is a very nice infographics by McKinsey last year. Here you have several metals there, and here you have technologies. Technologies traditional on your left, from geothermal, hydro, nuclear, and you see that the number of metals that you need is very limited. As long as you move to right, you have wind, solar, photovoltaics, hydrogen, the number of metals increases. You have more metals to use. But this is just about the number of metal. The question is, what about quantities? What about quantities? I could tell you several things, but let me just tell you one thing here. Renewables requires far less materials. 1 megawatt ground PV plant requires 2 tons of materials at the origin, okay? If you want to make the same electricity over 30 years, the lifetime of this facility, you need 14,000 tons of coal, so 70 times more. This to give you an idea what is the big difference between these two approaches. And this is recyclable. Carbon dioxide goes to the atmosphere, and that's it. Let's now go to the electric mobility. I want to be very practical. I am an electric driver for over 5 years. When I drive 300 kilometers on a motorway trip, I consume about 50 kilowatt hours. It corresponds to about less than 6 liters of petrol. If I drive the same road with a petrol car, I go to via Michelin, it tells you how much. It is 30 liters. So what is the reason why we have to move to electric mobility? Because to drive the same road, you consume between 3 and 5 times less compared to a conventional car. That's it. All the other reasons are interesting, are relevant, but the very most important one is this one. Okay, never forget. There is a radical difference between a conventional car and a battery vehicle. The conventional car is powered by a material input, gasoline, diesel fuel, and very simple product. The waste is dispersed in the atmosphere, carbon dioxide. Who cares? It's invisible, you cannot see it, you cannot taste it, so nobody cares, okay? Here, it is powered by an immaterial input, which is electricity, which you can do with renewables, and you do more and more with renewables. So as Francesco said, the electric car will become better and better over time. And there are several complex materials inside the battery, for sure, but there are no dispersion. You make your full load of metals only the first time when you buy your car, then it is always the same. And this one is a linear economy, this one is a circular economy, because the lithium of my car can be used by my children and grandchildren. And be careful, because when you talk about lithium batteries, there are different types of lithium batteries. You can take two cars with the same battery size, with two different chemistry of the cathode, NMC, nickel, manganese, cobalt, and LFP. The first one has about 50 kilograms of nickel plus manganese plus cobalt. The other one has zero. By the way, the other one is my car, has zero nickel, cobalt, manganese, and it has almost 40 kilograms of iron, which is not exactly a problem. Plus there is phosphorus, which is also not a big problem. I can provide details on this. But what about lithium? We cannot get rid of lithium. Do we have enough lithium? We get it from mines in Australia and from brines in South America. Estimated resources are 23 megatons. That's US Geological Survey. And in 2013, 10 years ago, now they are 4 times as much. How is it possible? Because we know we need lithium, we have been looking for it, and now we have increased the available resources. Out of these, 26 million tons can be exploitable now, economically speaking. So the question is, if I assume about 8 kilograms of lithium per car, how many cars can I make with 26 megatons? I can make 3.2 billion cars and vans. Today we have 1.4. So you see, these numbers are not so different. And so is it doable to make an electric car, for every car electric? It depends by manufacturers, how much lithium we will discover, how much lithium we will recycle. If there will be another technology, if the batteries will become smaller, because people understand that you don't need a big battery, that's an interesting topic. And then also we have the cobalt issue. If you have an electric car, people, your friend will tell you your battery, bloody battery, Africa. Well, there are reports of human rights abuses in the Democratic Republic of Congo, but people tend to forget that cobalt is absolutely needed and not replaceable in small devices, in mobile phones that everyone has, in robot, in lawn mower or stuff like this. And here, they are not replaceable. They never tell you about it. But let's look at the numbers. The big provider of cobalt is the DRC, Democratic Republic of Congo. 145 kiloton produced last year, 73% of the global production. About 20% is estimated to be the cobalt from DRC involving possible human rights abuse. About 40% of cobalt is used for automotive batteries. So with a very simple math, you can conclude that less than 6% of the cobalt extracted is ending in automotive batteries. So you see that how the myth, when you look at the numbers, becomes big myths and misinformation. So the question is, are there enough mineral resources for batteries? Because this is the question we want to answer. This is a projection of the International Energy Agency. There are different projections, but they don't look very much at the numbers. They estimate that the production increase for some selected materials for staying within 1.5 degrees is we need 40 times more lithium, 25 more graphite, 21 more cobalt. It's a lot. So people ask me as a chemist, do you think that we have enough? I think we do have enough, also because these numbers are going down day by day. The real bottlenecks are different. The real bottlenecks are exploration, permitting, extraction, refining, and products manufacturing. So it's not, people are focused on the resources. This beautiful planet is plentiful of minerals. But what is the real challenge, the real bottleneck, is are we fast enough to make the batteries, for example, the batteries or any other device we need? That's the big. So again, the problem, time. There is a potential game changer, which are sodium batteries. That's uncertain at the moment. This can change really everything. They have a lower energy density for physical limits, so they will be used. They would first impact the renewable energy sector where the volume is not that a problem if they become really implemented. And sodium is everywhere and can be combined with seawater desalination. We have another problem in this complicated world, fresh water. So getting sodium from the sea would allow you to have also seawater desalination. So difficult to make prediction, but stay tuned about this. So the hydrogen option, hydrogen is an option, but not for cars. Molecular hydrogen, H2, is overabundant on Jupiter, but we cannot go on Jupiter and take it down to the Earth. On the Earth, hydrogen is not existing, basically, and it's not an energy source, but an energy vector. So if anyone is interested in deepening this topic, I suggest to look at this lecture I gave on hydrogen last year. So why the hydrogen car is dead? 12,000 hydrogen cars sold, 12,000 overall globally. If you take a battery car, you have a renewable electricity to make it, and you put the electricity to the grid, and then you can charge the battery, and then you go to the engine and move your wheels. If you have an hydrogen car, the electricity is needed to make the hydrogen. Then the hydrogen needs to be sent where you can fill up your car. So you have to make it, compress, to liquefy, to transport, and then it goes to the fuel cells, and blah, blah, and blah, blah, and blah, blah. So at the end, in your electric engine, which is also the hydrogen car is an electric engine, to make the same road, you need 3 times more energy to make the same road compared to the battery vehicle. So why to use the hydrogen car? That's why that already. The hydrogen will be relevant for high temperature heat, like cement, so on. And as on the heavy transportation system, especially as an intermediate for liquid fuels. And just about liquid fuels, let me tell you one thing. What about e-fuels? E-fuels means making fuels through electricity. It stands for electricity. This is a pilot plant of Porsche in Chile. And you see, that's very small. We are at the very preliminary stage of doing these things compared to the industrial demand. So we are very far from large industrial production, and we have many problems to be addressed yet. The carbon feedstock, the hydrogen feedstock, you need to make hydrocarbons. You need hydrogen and carbon. Okay? So water. Okay, water in the desert, it's easy to get it. Technology, not clear which one. Energy and economical balance. What about environmental footprint? So, a lot of problems. And especially watch out that no improvements if you use e-fuels are made for motor efficiency, which stays at 75%. So you make all of this effort, and then you throw away 75% of your fantastic e-fuel. That's not very rational. And you don't improve the air quality in urban cities, definitely. Same as fossil. Same considerations. Similar considerations can be applied to biofuel. A final question, can I decarbonize my life? And I want to give you my example. We have seen example of very smart developments and cities and so on. Let me tell you how your electric house can work. I live in this house the last almost 2 years with my family. I have a photovoltaic 10 kilowatt plant system and solar thermal. With a battery, of course, to accumulate the excess production, and a geothermal heat pump. What is the result of this? This is the energy balance as of yesterday, since January 1. This house has produced 11.6 megawatt hours and has consumed 10.2 megawatt hours. So it has produced more energy than the one that has consumed. 25% almost of the electricity, I put it on the grid, so I'm ready for a community, for an energy community. I took some energy from the grid in these gray days, for orange part. So my overall self-consumption is 83%. I don't live in sunny Sicily, okay? I live in gray Po Valley like Milan. And imagine what can be these numbers in central or southern Italy or Spain or Portugal, whatever. Let me point out that 83% includes about 1,200 kilowatt hours for charging my car. So about 40% of my gasoline for my car, my electricity, is obtained via self-production. So there is an enormous room for expansion of this, millions of independent buildings all across Europe, and this is really the sleeping giant of energy security. People can be more independent, and companies can be. So the energy transition, I am almost to the end, is the greatest challenge in human history, because we have to make, in 30 years, a gigantic challenge that will change and reshape our economy. We have been in energy transition for over 2 centuries, but the transition from wood to coal took 1 century. Okay? We have to do it in 30 years, less than 30 years, and that's really a staggering challenge. So the good news is that the key technologies for the transition are already existing. We don't have to expect for a miracle technology. They are photovoltaics, batteries, heat pumps, hydroelectricity, biomass, and so on. You like it? You don't like it? Well, whatever it is, this is what you have. But this is the solution of the 90% of the problem. The rest, 10%, and the improvement of this is on the shoulder of science, of scientists, and of scientific and technological development. So this is, let us do it this, but trust us that 90% is already there. And these technologies are having an exponential growth. This is the exponential growth of wind, the blue, of photovoltaics, the yellow, of heat pumps and batteries. You know, they are going like this, like this. So the question is, what room there may be in 10 to 20 years from now for options that are more expensive, more uncertain, and more controversial? Because we are going like this. There is no stop in sight. And you have other technology going like this, and they tell you in 20 years, give you something. But, well, you know, so since the money is not unlimited, we have to consider seriously this point. Okay, so these technologies are changing everything. When there is an exponential growth, everything changes. And, well, time is our enemy, and speed is our obsession. And I try to summarize with a number what is the speed that we have to implement. The total installed photovoltaic capacity in Europe reached about 200 gigawatts last year. It should double by 2030. What does it mean? In practice, in the next 6 years, we need to match what we have done in the last 24. So we need to go 4 times faster. Will we be able to go 4 times faster with that technology, which is already rushing a lot? I don't know. We are unable to make predictions, clear predictions, precise predictions of the energy transition, of the technologies to be implemented, because there will be even unexpected happenings, possibly even very positive. But what we know very well is our objective. Our objective is to enable the energy transition, and we know that our objective is to phase out fossil fuels. And phase out doesn't mean phase down. Thank you very much.